learn, or we will get to know some more fascinating aspects of chemistry at the interface of biology. And before we move to the session, it is privilege for me to introduce our speaker today, because he's not only the speaker for this session only, he has been an integral part of this MSc Applied Chemistry program that our chemistry unit of Applied Science Department is offering for last 3 years. So he has been there from the beginning, and he has helped us a lot and guided us for the construction of this course curriculum, the program curriculum, and betterment in every Board of Studies meeting. So in that case, he is also the integral part of this unit in that way. So before I hand over to Professor Haldar, I would like to give a brief introduction about him. Professor Haldar received his BSc and MSc degree in chemistry from University of Calcutta. He then received his PhD degree from Jadavpur University, Kolkata, in the research area of molecular self-assembly of synthetic peptides in 2005. And then he had many prestigious international postdoctoral fellowships, like with Professor Ivan Hook at the Institut Européen de Chimie at Biology in France for the period of 2005 and 6. Then he moved to the University of Manchester, United Kingdom, for the second postdoctoral stay, where he stayed from 2006 to 7. And then he moved to Institute for Organische Chemie, University of Würzburg, Germany, as an Alexander von Humboldt Fellow for the period of 2007 and 8. On returning to India, he then joined as assistant professor and the group leader of the bioorganic supramolecular chemistry group at ISAR Kolkata, very near to us. And from there, he stayed, he was assistant professor for the period until 2013. Then he was promoted to the associate professor, and now from 2018, he is the full professor and the group leader of the bioorganic supramolecular chemistry group at ISAR Kolkata. Professor Haldar has several awards and recognitions from different academic bodies and institutes across the globe. Like he had the fellowship of French Ministry of Research from France in 2005, the prestigious Liverpool Trust Fellowship by the United Kingdom in 2006, then the very prestigious Japan Society for the Promotion of Science, the JSPS Postdoctoral Fellowship in 2006. And at the same time, he had the Alexander von Humboldt Foundation Postdoctoral Fellowship by Germany in 2006. In 2016, he got Young Talents Award from Crystal Engineering Communication, RSC, United Kingdom. And in 2016 as well, he got the Emerging Investigators Award by Journal of Materials Chemistry A, Royal Society of Chemistry. And his works spreaded over different fields like development of smart peptide-based nanostructured materials, and the amino acid analogs with tunable functionality, self-aggregating systems from pharmaceutical small molecules as delivery vehicles, very important ones, artificial light harvesting systems, and designer ion channels and crystals, and many more. Professor Haldar has published more than 120 papers in international acclaimed journals of high repute, and 8 book chapters and 4 books. And so far, 13 students have been guided to their PhD degree by Professor Haldar. Today, he will deliver his talk on the topic, the design, synthesis, and chemistry of advanced materials to mimic biology's adaptive properties. So with this introduction, I request Professor Haldar to kindly deliver his lecture and share the research with us. Over to you, sir.
Thank you, Professor Ghosh. Thanks for these kind words. And I thank Maulana Abul Kalam Azad University of Technology for organizing this nice webinar. That's exactly a very good program for the students as well as the faculty members and others interested in academia and research. And so as, I also thanks the administration of Maulana Abul Kalam Azad University for their support. And as Taposh has mentioned already, that I am from IISc Kolkata, and let me share this. So, can you see my presentation properly?
Yes, sir, it is visible, sir.
Okay, okay. Thank you very much. Yes, and our campus is just next to Maulana Abul Kalam Azad University of Technology. So we have a very green, large campus, near Kolkata, and with very nice facility, very good hostel that is very important for the students and their life beyond research. We have a nice infrastructure as well for research and other things. And so I welcome you if you have some time to visit our campus. Obviously, in this pandemic time, there was some restriction, but now we are opening slowly for everyone. And with this, what exactly I am doing in IISR Kolkata. So my group name is Bioorganic Supramolecular Chemistry Group, and we are developing designer synthetic amino acids. So that is our first priority. Till date, we have developed more than 25 amino acids on our own. So that is obviously the synthetic amino acid. And most of the amino acids, they contain a chromophoric system. So purposefully, we attach the chromophoric system to the amino acid so that we can study the amino acid by various spectroscopic techniques, whether it is absorption, emission, and other spectroscopic method. So, and there are few examples of that kind of amino acid that we have made in our laboratory, and we can make them in gram scale quantity. So, if anyone is interested about the amino acid, you can contact me. We will provide. And so, there's a very interesting part. And then we are synthesizing designer peptides and peptide mimetics using our own developed amino acid as well as various coded and non-coded amino acids that are available in market. And then we are studying the structure and function of the peptide and peptide mimetics. So we are working on both the biochemistry as well as the material science. So on both sides of the peptide and peptide mimetics. And we have many projects in our lab. So we are developing protein structure and function, targeting a particular protein motif, mimicking that protein motif by synthetic peptides. We are also developing nanostructure material using the synthetic peptides. So you know that the peptides, they have different folding pattern. They can fold in helix, they can fold or assemble in seeds-like structure. And using that motif, we can develop various nanostructure material. We can use the nanostructure material as a delivery vehicle for important drugs, other biologically important molecules. And then we are also working on a sustainable release. So it is not a fast release, but it is sustainable release. And we are using this kind of peptides or peptide mimetics to develop stimuli responsive gels, and as well as a synthetic receptor. So the host guest complexation with this kind of peptide and peptide mimetic, conducting material and light harvesting system. That's also very interesting thing. So the peptide can be used as a light harvesting system. So you can absorb light as a lower frequency, you can emit at a higher end, and like that, or the vice versa. And then we are working with the porous organic material. So where you can develop the porosity in the material, you can develop the channels in some materials, and then use them for the gas storage or other materials as a storage purpose. And we are a little bit working on amyloidogenesis and its inhibition study. So that's the projects at this moment we are dealing with. And we believe that a very little change in atomic level that has a huge impact on the property of the molecule, on the structure as well as function of the molecule. For example, say we have developed one foldamer. So that's actually a peptide mimetic. So where we have used meta-aminobenzoic acid, a very common and simple reagent for any chemistry laboratory. And we have incorporated uh, urea with that meta-aminobenzoic acid to develop the column. And the thing is that when we got crystal, we found that the compound actually formed a duplex structure through intermolecular hydrogen bonding interaction, and that's very interesting. And then what we have done, so we have replaced one of the hydrogen of meta-aminobenzoic acid with the bromine. And what we found that the duplex structure still exists, but now there is a halogen bond. And actually this halogen bond is helping to make the material phosphorescent. So we have studied that phosphorescence properties in solution, in solid state by different spectroscopic techniques and details, and we found that this heavy atom effect, the incorporation of the bromine, is actually responsible for the phosphorescence property of this kind of polymer. And then we thought, okay, so from hydrogen to bromine, we have got a phosphorescence. So if we incorporate a heavier atom, heavier than bromine, so let's say iodine, maybe the phosphorescence property will be increased more, and maybe we will get a phosphorescence for longer time. But unfortunately, when we got the crystal structure, we found that yes, the duplex structure is present there, but the incorporation of iodine due to size exclusion, so there is no halogen bond at all in the molecule, and the molecule lost its phosphorescence. So that's why I say that we believe that very minute change will affect a lot on the structure and function of the compound. And then we have extended that study. So instead of one meta-aminobenzoic acid, we have incorporated second meta-aminobenzoic acid. And now it is a longer oligomer, and we found that from different spectroscopic studies, from like the 2D NMR, concentration dependent NMR, temperature dependent NMR, NMR solvent titration, that actually there is a double helical structure exists. And finally, we are able to crystallize that material, and we found that actually when there are two meta-aminobenzoic acid units, the molecule adopt a helical structure, and two such molecules just intertwine through intermolecular, or better to say interstand hydrogen bonding interaction, as well as interstand pi-pi stacking interaction. And thus the double helical structure is stabilized. So this is actually a mimic of a natural double helical structure, where we will see the this kind of intermolecular hydrogen bond or interstand pi-pi stacking interaction. Not only the change in atomic level, but if we also change the environment, that's also huge impact on structure and function of molecules. Same molecule, so that compound we have already made with two meta-amino benzoic acid units. If we placed in chloroform, actually it's from double helical structure from chloroform. But if we change the solvent from chloroform to methanol, now we found that it's no more double helix, rather it is the anti-parallel sheet-like structure that is forming. So the environment also has huge impact on structure and function of the molecule. Okay, so let's go for some fun rather than more seriousness. And so we all have seen the spider net, basically the spider web. In the yes, in this time, in this winter time, if we go to garden in the morning, we'll see a lot of spider web, and that's sometimes really it's not good if you are basically a morning walker. So you have to go through the spider. And but we also realize that by 8 o'clock in the morning or 9 o'clock, when there is strong sunshine, actually most of the waves are gone from your garden. So there's almost nothing. So that means these kind of compounds, they have some relationship with the temperature fluctuation as well as humidity. So when there is much more moisture, the spider web exists, but when moisture is less, you see that the spider web from your garden is disappear. And we have mimicked exactly the same property of the spider silk and spider web using a synthetic molecule. So for that purpose, we have synthesized three compounds. So basically, this is a diacid. And with the diacid, actually, we have incorporated leucine and tyrosine. So for the first compound, we have incorporated leucine on both sides of the diacid. For the second compound, we incorporate leucine and tyrosine at each end. And for the third one, both sides, this is tyrosine. What we found that when it is both sides leucine or both sides tyrosine, the compound is solid. But when one side is leucine and one side tyrosine, it's a gummy material. It's not solid. And we have tried many methods to crystallize the material, but it's not. But why do we realize that at 20 degrees centigrade, with a certain humidity, we can utilize this compound containing leucine and tyrosine to make a spider silk-like material. And so in the this panel A, actually, this is the spider web made by this material in our lab. So you can use a spatula, or you can put the compound in injection syringe, and you can use that injection syringe to make the spider silk. And in panel B is the natural spider silk on the window of my lab. And so it's very difficult to distinguish between them. We have also studied by microscopic techniques, polarizing optical microscope, and we have seen they are showing exactly same optical properties. And then we have studied by biology and obviously by electron microscopy, and we found that actually this compound is making is forming by nanofiber, and that nanofibers are made of several small fibrils. So fibrils, they are first formed, and then the fibrils they assemble to make the nanofiber. And this kind of fibers, they can actually bear some amount of weight, like the natural spider silk or spider web. And then we have studied by all different spectroscopic techniques like this FTIR-11, and we have developed a model how this material self-assemble to mimic the spider silk and spider web. Okay, so now I will come to this topic, that is the biology's adaptive properties. Obviously, the example I have already shown, we have adapted the property from biological system. And so biology's adaptive properties of materials, basically the nanomaterials. So this is a multidisciplinary research area, truly multidisciplinary one. And it is the creation of novel material devices uh, and understanding, or better to say, control their structure and function at nanoscale. That means 1 to 100 nanometer scale. And sometimes we got a new functionality in that nanoscale rather than the bulk material. So that is also very important. And this biologist adaptive material, it is actually a combination of two advanced field nowadays, we can say, basically the nanotechnology and biotechnology. So first we follow what happening in nature, and then we try to mimic that in laboratory using nanotechnology. So it fabricates devices for studying biological system, maybe cell, maybe tissue, or maybe some biochemical properties, uh, like this diagnostic, therapeutics, regeneration. And this kind of material, advanced materials, they have application in bioengineering and as well as medicine. Okay, so as we are talking about nanomaterials, so let's for the students clear the part. So what we are calling nanomaterials. So obviously, from the term we know that 1 nanometer is 10 to the power minus 9 meter. It's billion of a meter. And for reference, so if we take a A4 size paper, so the thickness of the paper is 1 lakh nanometer. That's a huge one. For a human here, it is 10,000 nanometer, and but the nanoscale we are talking about, that is only 1 to 100 nanometer. And if we take on this scale, we'll see that actually water molecule is 10 to the power minus 1 nanometer. A glucose close to 1 nanometer. And then this antibody and virus, they are from 10 to 100 nanometers. So that is actually the nanometer window what we are looking for. And then all other things, the bacteria, cancer cell, just a dot from a pin. So they are quite large from this side. And so this window we are interested about, this nano window, 10 to 100 nanometer. Okay, and then what is the application of this biology adaptive nanomaterial? So we can use them for the nanopore technology. So nowadays, that we have several water purification system where we use this nanopore technology, even desalinate the seawater to produce drinking water. So that's the very important part of this kind of nano porous material development. Or we can use them for nanomedicine. So actually, the drug we are taking. So instead of bulk medicine, if we convert them into the nanomedicine, that will be more helpful as it is expected. And molecular nanotechnology, so where we develop a single molecule to use as a molecular machine, and we call them as a molecular nanotechnology. And then in diagnostic, in therapeutic, tissue engineering. So this is just an image from Google that how we can prepare a soft nano robot, and that can drive inside our blood vessel or even in the lungs, and that can act for this particular purpose. Okay, and so in the diagnostic again, so their important parts are the imaging. So that's very important. So when we take some picture, snapshot from a microscope, contrast is a very, very big thing. So contrast in imaging is very important. And previously we used different kind of dye for this as a contrast tool, but nowadays we have developed many quantum dots. So who are better contrast agent for this kind of imaging. Or it's also helpful for microscopic sampling. And for therapeutic, we can use this kind of biologist adaptive material for drug delivery purpose, for killing bacteria, virus, cancer cells. So they are in right hand side some cartoon diagram from Google. We can repair the damaged tissue. We use them for oxygen transport. So just in this COVID situation, that research was very, very important. So if we use some synthetic molecule, and that can be better oxygen transporter than the biological system, we can use them when there is a deficiency of oxygen, or when your body cannot carry much amount of oxygen, body fluids. And then the skin and dental care, obviously, we can use this kind of nanomaterial for that purpose. And clot removal, that's also very important for our system. Okay, and then the therapeutic applications. So basically, it is the delivery of the medicine to exact location. So that's very important. And for that purpose, we have developed various kind of dendrimers, capsule, microsphere, and this kind of wrapping, or better to say, formulation, will reduce the side effect. And due to this synergistic effect of this wrapping, this formulation, sometimes the drug works better. And so destruction of harmful organism by interrupting their division process. So we can do this with this synthetic material. And that's I have already discussed earlier side, the transport of oxygen by global light blood cells. Okay, and there also we can apply this system for therapeutic purposes, like removal of dead skin, or excess oil for skin care, or apply for moisturizing compound dental care. So we can utilize this kind of system, biology's adaptive system. Okay, and now the question is that, so is it really possible to make such kind of soft devices following the biological system? And so I'll share this slide, and the answer is yes. So actually, this three-person, Sauvage, Stoddard, and Ben Feringa, they received a Nobel Prize in 2016 by making this kind of soft robot following the biological systems. So that is the catenin, where two molecules just interlock each other. And depending on the environment, the condition, these two rings can move around each other. So this is, we can say, one kind of molecular meshing. So one molecule can rotate inside another molecule. Or here the real molecular meshing, the rotam. So where you have a wheel and an axle, so you can rotate the wheel around the axle. Or this is the nano car, the really the molecular car. So where depending on the external stimuli like light, you can move the car. So that was the development. So yes, it's possible to make the soft robotic material that can actually uh, follow the biological system, or that can mimic the biological system. Okay, so for this purpose, so what are the basic material or building blocks that we can use to mimic the biological system? So obviously we can use the liposome, we can use the dendrimers, porous material, carbon nanotubes, graphene, quantum dot, and peptide and peptide-based material. And so the different structure this material can form, they can form a vesicle where we have the solution inside, or they can form a micelle, a ribbon, nanotubes, nanofiber, poroid, or nanosphere. So these are the very important biologically adapted structure that we are trying to develop. And for liposome, so we all know about the lipids and phospholipids. They form vesicles of 50 to 100 nanometers. So this is the schematic of a lipid. So where we have the hydrophilic interior, and obviously the hydrophobic exterior. And then there is a bilayer structure. So we have that internal aqueous phase, and so these are the excellent circulation, penetration, and diffusion properties, this kind of liposome. And we can mimic this natural liposomes by peptide or peptide mimicking. Now, the liposome not only used as a carrier, but they can be directly acts as a drug. And nowadays in market, there are many liposomal drugs. So where the drug itself acts as a carrier and drug. The liposome itself acts as a drug. And the applicability of this kind of liposomal system, the microsphere or nanosphere. So they have very good exterior hydrophobic properties. So they can actually travel through our blood vessel. They can go beyond the blood-brain barrier, or pass through the vessel to the cell, and so on and so forth. But there is some restriction. The size is a very good thing in that case. So if you make some nanoparticle, or the vesicle that size more than 100 nanometer, then obviously it will not pass through your blood vessel. And but for the cancerous cell, they are porous in nature, and if there is a tumor tissue or cancerous tissue, and then obviously you can utilize this kind of liposomal particle to pass through the blood vessel. So they have some advantage. Advantage is that you can manage the hydrophobic and hydrophilic nature, and you can play with that, and characterize them by chemically and physically. They are biocompatible. You can use them for the drug delivery vehicle and control release. Can guide them to localize, so the exact position before the drug release. You can guide them, and you can administer them by various routes. So whether this is by injection or oral, or help to avoid the toxicity. So if it is a naked drug, it is more toxic. So, but if you can wrap it up and delivery in particular site, you can avoid the toxicity. And there are some disadvantage also. Sometimes there is some leakage, sometimes the high production cost, and all these things are there. Okay, so as I said that we can mimic this liposomal material by peptide or peptide mimetic. So first we have developed a pentapeptide, so containing leucine, AIV is the alpha amino isobutyric acid, and phenylalanine. And what we figured out that the peptide is actually forming nanoparticle, and that we measure by DLS, and with increasing peptide concentration, actually the particle size is increasing. And we have started by microscopic technique like the FESA and AFM, and we figure out that the peptide from microsphere, and it's not only microsphere, it's the porous microsphere. So there are pores on the surface of the peptide microsphere. And we have also the solid state structure of the peptides, and from where we found that the peptide actually adopt a helical backbone conformations, and that helical backbone conformations, they further self-assemble to form a bundle of helix-like structure. So this the helical backbone conformation or the self-assemble to form a helical bundle structure, and which actually further self-assemble to form this kind of spherical material. And we use this spherical peptide nanosphere for drug delivery purpose. So this is the drug molecule, sulfamethoxazole. We incorporate inside the vesicle, and we have studied by different spectroscopic techniques the attachment of the drug inside the molecule, and then it's the release of the drug with time in phosphate buffer. And so, yes, it's possible that you can mimic the liposomal system with a peptide or peptide mimetic. And then another example where we have also done the same thing. So now we have taken a different peptide with much more flexibility, and so these peptides also form this microsphere structure, and there are four inside the molecule, so we can use this four to for the drug carry. And so this porous material we have studied by different microscopic techniques like atomic force microscopy and scanning electron microscopy. And so you can see that the pore on the microsphere. And so then we have tried this anti-conversion and mood stabilizing the carbamazepine to capture inside the vesicle, to put that drug inside the vesicle, and then use them as a delivery vehicle. So we have also studied their control release different conditions. And okay, so this is a particular case where I want to mention. So here we have developed a peptide mimetic compound. So here we have urea derivative with a diacid, pyridine dicarboxylic acid. And this compound is also form this kind of vesicle. And what we have seen that these vesicles are porous in nature, so we can incorporate a drug in this vesicle. And important thing is that yeah, this is a solid state structure of the molecule, how it's developed the vesicles and all these things. And the important thing is that, so when we put the vesicle with hydrogen peroxide, actually hydrogen peroxide ruptured that vesicle. And we use that property of the vesicle to carry anti-cancer drug. So we know that in cancer side, actually it is there large amount of hydrogen peroxide are present in cancer cells. So if we can make a delivery vehicle that is sensitive to hydrogen peroxide, Then the delivery vehicles, if we can encapsulate some drugs inside the delivery vehicles, the delivery vehicles will carry the drugs in the particular site, and then depending on the concentration of hydrogen peroxide, that delivery vehicle will rupture and it will release the drug at that site. So that was the idea. And we have studied that, and we found that yes, it's working fine. Actually, the delivery this compound we can use for carrying anti-cancer drug, and the drug can be released with presence of hydrogen peroxide. And if more or higher concentration of hydrogen peroxide, drug will release faster, and if hydrogen peroxide amount is less, drug will release slowly. So we have studied that, and shown all this by different microscopic and spectroscopic techniques. Okay, and now about the dendrimer. So they are also another natural molecules, so the dendrimer. And that kind of molecule, actually, we can say they are the giant molecule. And so in each dendrimer, there is a core, and then there is a internal cavity space for molecular cargo. And depending on the size, so we can specify the dendrimer as a first generation, second generation, third generation, like that. So how the size of the dendrimer is increasing. And also we can specify them depending on the surface group, so whether they are the hydrophobic or whether they are the hydrophilic on the surface. So on that. And in the right hand side here is a chemical sketching diagram of a real dendrimer, how it's look like, what's the functionality. So mainly you can see this is the amide, or yes, the amide functionality to make the very big dendrimer. So easily we can use the peptide or peptide mimetics to make this kind of dendrimer systems. And so this is just the schematic diagrams and some for the students. So how we can develop a dendrimer from the building block, starting from the building block. And so it is a two-step process: activation of functional surface group and addition of branching monomer units. So first we need to think about, so which one is the center, so from where we are going to start the dendrimer, and then it's just the functionalization of the surface, and so we can develop a bigger one, bigger material. Okay, and there are also another approach, so where we can make a part of the dendrimer, and finally we can bind them to the central moiety. So this is a different approach, convergent, where we can make the dendrimer. But for both system, for the direct and this convergent method, so there are some positive side and some negative side. And it's really speaking that the purification of dendrimer, a very pure dendrimer, making a very pure dendrimer is really difficult, because once you make your dendrimer, so there are different cavities that can accumulate different solvents or unreacted materials and rest of the thing. So it's very difficult to purify a dendrimer on its form. Okay, so we have tried to mimic some dendrimeric systems using our peptides. So this is the central core for this system is the benzene tricarboxylic acid, as you can see. And then we have actually coupled the amino acid. So these are the amide bonds. And so for this purpose, we have used the amino acid without any side chain. So these compounds are completely achiral. And we have used beta alanine and gamma amino butyric acid. So when n equal to 2, it is beta alanine, and when n equal to 3, it is gamma amino butyric acid. And what we have seen during this concentration dependent in vivo studies, we have seen that with the increasing concentration, so there is some shifting of the peak. So which says that there is a J type of aggregation of this compound. As we have studied also by FTIR spectroscopy, and there is also showing that hydrogen bonding aggregation in the molecule. And when it is beta alanine, the compound uh, fails to form gel in any organic solvent. But when it is gamma aminobutyric acid, the just change of one CH2 group, the compound form gel in many organic solvents. And we have studied the gel by geology and other experimental processes. We have studied the gel melting also. And then we are looking what what's happening. Just a change of one CH2 functional group, and why there is a huge change in the property of this dendrimeric peptide. And we figure out that so with this temperature dependence NMR, that there are some change in cell assembly pattern for both these compounds. And so then we have also checked by scanning electron microscopy, and again we have seen that when it is beta alanine, the compound is forming a nano rod-like structures, and that are not entangled. But when it is gamma aminobutyric acid, the compound is actually forming a fibrous material, and which are entangled to each other, connected to each other, and actually that helps to form the gel. And finally, we got the solid state structure of this compound, and it's appear that so when it is beta alanine, this compound actually stack on top of each other to form a helical structure, hydrogen bonded helical structure, and or we can say it's a columnar structure. And this is from the side view, and this is from the top view. For the second compound, the gamma aminobutyric acid containing compound, here also we are seeing that the molecules are self-assembled on top of each other to form a columnar structure. But if we see from the top view, we will see that there is actually difference in organization of the side chains, difference in organization of the functional groups. And that helps these two molecules to show different properties. So for the first molecule, when there is a beta alanine, actually it's a honeycomb-like cell assembly pattern, and there is any hardly any space to adopt the solvents. But when it is in gamma aminobutyric acid, there is hydrophobic interaction, there is cavity between the hydrophobic functional groups, and so that helps to form the gel. Okay, so further we have developed one more kind of this dendrimeric thing, and so here also we use the benzene tricarboxylic acid as the central core, and then amino acid like this tyrosine or this cysteine, sorry, methionine for this amide linkage. And again, what we have seen from different spectroscopic techniques, that these two compounds, when there is tyrosine and there is methionine, they are not showing the same properties. So there's something different. And so what is the difference and how the difference appears? So both the compound is CC symmetry, and there are amide functional groups. So same kind of hydrogen bonding functionality. Then what is the difference? The central core is same. So what do we figure out that? So when there is a methionine unit, actually the compound maintains CC symmetry properly. But when there is a tyrosine unit, due to steric hindrance, these three tyrosine moieties are not on the C3 symmetry. Rather than two tyrosine moiety is one side of the benzene ring central plane and one tyrosine just opposite side of the benzene ring. So the molecule basically lost its C3 symmetry, and then if we check the central amide core, we'll see. So when it is methionine, this CONH, this central amide functional groups, they are actually perpendicular to this central pores. So these units are perpendicular to the central pore. And that helps to form intermolecular hydrogen bonding when the molecules are just on top of each other. And this hydrogen bonding actually helps to form a columnar structure. But when there is tyrosine, these amide functionality are on the plane of the benzene ring. And so you can see here, so these amide linkages are on the plane of the benzene. And actually that restrict the hydrogen bonding between these molecules. And so when this molecule, again, it's lost its C3 symmetry due to the steric hindrance of the tyrosine units. And basically, in higher order structure, where we find that one molecule is surrounded by 8 other molecules, and that makes a cage-like structure. And there are enough pores in the cage. And so this is the packing structure for both these molecules. We have also studied by atomic force microscopy, and we have figured out that for methionine containing molecule, actually these are columnar structures, these are rod-like, rod-shaped morphology. And when there is a tyrosine, it's a porous structure. Actually, that porous material develop because of this loss of C3 symmetry and packing of the dendritic. We have also studied by nitrogen short-term experiment, and where we found that the tyrosine containing compound is showing very big nitrogen absorption at which is, I will say, quite high for this kind of peptide molecule and or organic molecule. Though nowadays many porous organic material or crop material has developed, which has a high nitrogen absorption potential. Okay, and then we have developed another peptide material, that's pentapeptide, to make this kind of porous material. So here again the peptide forms a supramolecular helical structure, and the supramolecular helix further self-assemble to make a helical bundle structure. And that helical bundle structure is actually helps to form this kind of long fibrous structure, but there is no pore in the material. And if we use a little bit of water and the peptide in organic solvent, then we figure out that the actually presence of little bit of water helps to develop the porous material from that kind of hydrophobic system. So here the supramolecular peptides that form the supramolecular helical bundle, no pore, it's a complete hydrophobic system. But if you make the material in presence of little bit of water, now we reach a material where the material is porous in nature. And so the porosity of the material we have studied by different techniques like the iodine vapor absorption. So you can see this is the crystal of the molecule. So when you use the crystal, treat with iodine, hardly is the iodine absorbed on the crystal. The yellow color, maybe a little bit iodine on the surface of the crystal, but when we make the material in presence of water, we make a porous material, and now the porous material can absorb huge amount of iodine. So this kind of porous material we can use for removal of the toxic dyes from industrial outlet water. So we have okay, and then the further biology adaptive material are the carbon nanotubes. So, and we know that the carbon nanotubes, they are the cylindrical coaxial graphite sheets. And so the carbon nanotubes have excellent mechanical strength and electrical properties. So, and they're semiconductive in nature. And nowadays, you know that the carbon nanotubes can be used for very, very different purposes. And they're actually very good materials for modern. And so we can use them for drug delivery, for cancer treatment, for cardiac regulation, matrix for tissue engineering. For many purposes, we can use this kind of carbon nanotube. And the second thing that nowadays people are interested about, so that is the graphene. So if you just cut the carbon nanotube in the length, also you will reach in a graphene. And the graphene, they are the strongest material, most stretchable and transparent material. You can record thermal conductivity, highest current density, they can conduct electricity, and very good flexible and wearable device you can make from the graphene. And other than that, you can actually use graphene as a base for many biologically important chemicals. So you can wrap graphene drugs with graphene, or you can put your antibody on graphene surface, and then you can use that for some kind of sensing property, or you can use the graphene for imaging purpose. So this is one kind of thing. And the next the thing is that quantum dots. So quantum dots nowadays we can use for imaging purpose and many other purposes. So this is also a very interesting material that now we can use in different purposes. So these are the basically fluorescent semiconductor nanocrystal from 2 to 10 nanometers in size. And depending on the size, the same compound, same chemical structure can show different colors. So that is the beauty of this kind of quantum. So when you are making a quantum dot, you have to be very cautious that you are making them very close in size. Otherwise, if it is a dispersed size, then it's very difficult to use that kind of quantum. And so they are excellent contrast agent for imaging and excellent level for bioassays. So we can use this kind of quantum dots for different bioassays. Using this. Okay, so in our laboratory, we have also developed this kind of quantum dots. So very specific in size, and they are showing very specific emission. So we can use them as a contrast agent. Okay, so for making that specific size and shape quantum dot, we have developed a few peptide and peptide mimetics. So like here, we have developed a tripeptide. This is also tripeptide. And depending on what kind of amino acid building blocks we are using in the peptide can form different structures. So like here, the peptide actually form a beta turn structure. So the beta-turn structure is further self-assembled through intermolecular hydrogen bonding interaction to form a matrix. So this matrix structure we will use further for the development of the quantum dots. And here again, we have used a king-like structure. The peptide itself has a bent structure due to the central aromatic ring and this 1,3 position substitution. And this can form a duplex structure by intermolecular hydrogen bonding interaction and a different kind of matrix from this peptide mimetic we can develop. Okay, so now coming to this morphology. Yes. So when the peptide was a beta-turn structure, and that actually formed a tape-like morphology. So you can see it's a nice tape-like morphology as is seen from the atomic force microscope. But when this is a duplex structure, so it's a different matrix, and you can see it's a sheet-like morphology, layer by layer morphology. So we have different morphology from two different peptides. And now we have also checked with FESM, the scanning electron microscopy. So when this is the beta-turn containing peptides, so it's basically shows this kind of tape-like morphology. And when it is this duplex is formed, a layer by layer structure. And now we have used these two peptide mimetics to form cadmium sulfide quantum dots. And from the UV visible spectra, we can see that quantum dots are formed and on the matrices. And here, further we have seen from atomic force microscopy that actually these spherical parts are the quantum dots, and that's embedded on the peptide matrices. So the spherical part, they are quantum dots embedded on the peptide matrix. And here also for the second peptide, the quantum dots are embedded on the surface of the layer-like structure. So the peptide layers are actually covered by the quantum dots, and they are very, I will say, uniform or close in shape and size. And so we have studied by different spectroscopic techniques. There are optical properties and all this stuff. And here you can see the emission of the quantum dots. So they are very bright blue emission. So we can use this kind of quantum dots embedded peptide matrix for imaging purpose. Okay. Then we thought, can we actually differentiate the quantum dots so the image will be much more contrast. So if we can capture a single quantum dot instead of the quantum dots spreading on the peptide mimetic tape or spreading on the matrix. And for that purpose, actually, we have developed this dendritic system, dendrimeric system, with benzene triamine core, and then aspartic acid and glutamic acid at the surface. And what we find that actually this kind of dendritic system, so from solid state, they can form a ball-like structure. So this is the single molecule, and here we can see the 3 aspartic acid or 3 glutamic acid, and with that they can form a ball-like structure. And so if you put two such ball-like structure, then you will you will get a capsule-like structure. So that is the capsule. So it's a single ball, and then you put two balls together to get a capsule-like structure. And that was the design. So we wanted to put one quantum dot inside the capsule, so that it can act as a better contrast level. And so, yes, we have developed that kind of capsule, and then we have developed the quantum dot. It's from the microscopic and spectroscopic techniques, we can figure out that the quantum dots actually go inside this kind of capsule. And we have further studied by confocal microscopy to figure out the contrast property of this kind of quantum. So we can use this quantum dot for imaging purposes, biological imaging. Okay, then there are metallic nanoparticles. So I can skip this part for today. So just for one information, that recently there is a report that the metallic nanoparticle, basically the gold nanoparticle, can be used to treat Alzheimer amyloid plaque. So this is really amazing, and a new start to fight against Alzheimer disease. So, okay, then there are magnetic nanoparticles. So, if you prepare magnetic nanoparticles, they also be used as a MRI contrast agent. They can use for excellent bioassay and targeted delivery. That is the important part. So we have developed some magnetic nanoparticles, though we have not used them for targeted delivery or any bioassay. But I just want to show you how they work, and what we are speaking about, that a magnetic nanoparticle you can use for targeted delivery if it is really works in solution state or not. So here we have used a peptide actually that contain a nitro functional group. And so using that peptide with nitro functional group, we have developed magnetic nanoparticle from iron. And so this magnetic nanoparticle, Fe3O4, basically, is at the center, and the outside, actually, the peptide one is reduced the iron, it is now converted the nitro functional group to amine functional group. And that amine functional group is stabilize the magnetic nanoparticle. So your peptide is wrapping the magnetic nanoparticle. And we have developed that nanoparticle, and actually we have used that magnetic nanoparticle to embed palladium and do Suzuki coupling reaction. And but what we want to show, that after reaction you can just separate the magnetic nanoparticle embedded with palladium using an external magnet. So when your magnetic nanoparticle is in solution, if you use external magnetic field, you can move that magnetic nanomaterial in solution from one side to another side. And using the same technique also, if you want to wrap a drug in your magnetic nanoparticle, if you inject inside body and then use external magnetic field, obviously not very big magnetic field, so you can move that magnetic nanoparticle inside your blood vessel. So that is possible. That's what I want to show you here. So we can develop this kind of system. Okay, and so the next part is again the biology adapted material. So we have seen that there are many hydrophobic surfaces in biology, like that lotus leaf and all this stuff. So they are excellent hydrophobic material. And so we are planning to make such kind of material by mimicking peptide system. So here what we have done, this is a diphenyl alanine. So two phenylalanine units connected. And then we have connect this diphenylalanine, a small dipeptide, with POS. So this is a silicon containing material. So here we have an amine function group. So it's a very simple one, just amine and acid coupling. So we got an amide and it has a POS material. So now you can see this silicon containing material. This is hydrophobic in nature, and also they are butyl function group. So that's also hydrophobic in nature. So once we make the material, we have studied their self-assembly pattern because it's really a big functional group in comparison to this peptide system. And so how they will self-assemble and all this stuff. So we have studied by different spectroscopic techniques. And we figure out that actually this material, they form anti-parallel sheet-like structure. So they just self-assembly in anti-parallel sheet-like structure. And but surprisingly, when we study the morphology, what we found that when it is only the diphenylalanine dipeptide that form a nanotube-like structure, the tubes are perfectly hexagonal. I don't know how they self-assemble in this perfectly hexagonal nanotube-like structure, but they do. That is the reality. That is the experimental data. So what we propose that actually they form an antiparallel sheet-like structure by intermolecular hydrogen bonding interaction, and then the sheet folded to form this hexagonal structure. But general conception is that if a kind of structure fold, that will make a tube-like structure. So that is not this kind of hexagonal structure. Anyway, so this is the structure from naked peptide, and this is the structure from the POS, the polyoxysilol. So when there is no peptide, only this this material, this silicon containing material. So they actually form this kind of nice cubic structure, very well, cubic structure. But when we put them together by covalent bond, now we find that they are actually making spherical structure. But sphere are very unique in size. And so that was the first thing we have seen, that they are changing their morphology. And now we just use simply paper and broadcast that hybrid compound on paper. And we found that now the paper is repelling water. So even if you fold the paper and put it in water, take it out, and the paper is unfolding itself. So it completely repel the water. And we have studied by scanning electron microscopy, and we found that now this hybrid compound microsphere is actually on the surface of the cellulose fiber of the paper, and that makes this paper very much hydrophobic. Not only hydrophobic, it increases the mechanical strength of the paper, huge mechanical strength change for the paper. And then we have studied with atomic force microscopy, so how the microsphere covering the paper surface, all these things. Okay, so then we have used this kind of hybrid compound coated paper for antibacterial paper. So we use E. coli, so whether the E. coli can form a colony over the paper. And we found that when the paper is not coated, it's the normal paper, these bright spots are actually the E. coli colony on the paper surface. But when the paper is coated with the compound, there is no E. coli colony. So the paper now we can use for packaging purpose, where we need to restrict this kind of by bacteria kind of thing. So this is a good packaging material, we can say. Okay, and more important thing is that, so this kind of hydrophobic material we can use to protect the metal from corrosion. So for this experiment, we have taken this iron nail. So these are the raw iron nail, and we have covered half portion of the iron nail with our hybrid compound, and then we put that iron nail in water, and what we have seen that the covered part of the iron nail, so there is no rust, but in the other part, the naked part of the iron nail, so it got rust within 24 hours. And so what we realized that this our developed hybrid compound that can protect the raw iron from rusting. So this is a huge impact for future applications. And not only iron, we have also studied with silver article. So we know that silver is very sensitive to hydrogen sulfide. Even if you use silver ornaments for a long time, due to presence of little amount of hydrogen sulfide in atmosphere, in air, so the silver ornament will take black color after few days due to formation of silver sulfide. So we have just protected a silver artifact, that half portion we have protected with our hybrid compound, and the rest half is naked, and we put it in hydrogen sulfide uh, atmosphere, and we found that the naked part is turned quickly silver sulfide in presence of hydrogen sulfide, but the protected part, the covered part, is intact. And even for that iron nail experiment, we have tried in a drastic condition. So we put that nail in sodium chloride, potassium chloride, that is the saline water, potassium bromide, even in HCl, and you can see that even in saline water or even in HCl, that our hybrid compound is able to protect the metal from corrosion. So this is very interesting for further future application. And finally, we have used that material to resist fire. So it is known that that kind of polyoxosilicon POS material that can repel fire, retard fire. But when we make that hybrid compound, it's actually diffusing fire. It's stopping fire. So how it works? So we have done a very simple experiment. So this is a matchstick. So we have covered half portion of the matchstick with we have coated half portion of the matchstick with our hybrid compound, and then we have done this experiment. So when the matchstick is not coated, the entire matchstick is just burned. Uh, we have coated matchstick with our naked peptide. So it is not the hybrid, it is only the diphenylalanine. Again, the matchstick completely burned. So we have coated the matchstick with the POS, the polyoxosilicon, that material only. So what we have seen now, the fire has captured, but again the matchstick completely burned. So it's not stopped the fire. We reduce the flame and not stop the fire. But when we use this hybrid compound, we can see the fire just stop at the coating, and it's a, so we can use this kind of biology adapted material for different practical applications. And actually, we got a patent on this material, and we are developing some industrial application of this kind of material with a company. And let us see if we can help the society on that. Okay, So the next important thing I discuss that is the treatment of water. So water is also very important for our environment and everyday life. So, but due to industrialization and the misuse, obviously, the water is now contaminated a lot. So I think in future there will be battle for pure water or better water, uh, which we are now we are not realized nowadays. So to clean the water, we have developed one Jupiter ionic compound. So first, I need to explain. So what exactly polluting the water? So if we check polluted water, we will see. So there are organic material like different organic dyes from the industries or the petroleum products, and as well as there are metal and non-metal parts. So inorganic salts are also huge amounts of salts, metal ion or anions are present in the water, and that makes the water contaminated. So we need to remove both the positively charged ion, the negatively charged ion, as well as the organic compound from the water. So for that purpose, we have designed a peptide mimetic compound. So where we have hydrophobic functional groups. So that hydrophobic functional groups can take care of the organic pollutant. We have the positively charged section, so that can attract the anions. We have negatively charged section that can attract the cations. And by that way, so we can remove all the anions, cations, and organic dyes or organic oils from the water. And that's why I call this the mopping up oils and ions from water. Okay, so the system is very simple. So the ingredients are very common. So this is the picric acid, 246 nitrophenol, and this is the DCC. So generally we use as a coupling reagent for amide bond formation. So when we put them together, immediately they form a very bright orange color compound. So we have studied the compound by various spectroscopic techniques, and obviously we have the crystal structure of the compounds, and from that we can say that it's a deuterion compound. So there is a positive charge, there is a negative charge, and as well as there are the cyclohexane units. So they are the hydrophobic functional groups. And so we have used this compound for first sensing different metal ions and anions, and what we have seen that they are doing very well to sensing these metal ions and anions. So here you can see we have tried with various anions and cations, and so these are sensing the metal ions and anions aqueous medium very nicely. Okay, and then we have utilized that property to clean the water from the metal ions. So first here what we have done, we have taken the compound and we have dissolved iron salt in water, and then put that iron salt containing water with the compound, just shake it and then separate the filter the water, and we found that it's a completely clean water, no iron is there. We have also tried with our campus tube well water. So we have taken the water from the tube well from campus, and we have seen that if we put that water for 2-3 hours, it's turned slight yellow color due to presence of iron. And so we have treated that water with our compound, and then we can say so there almost no iron, so no coloration. We have prepared a column to filter that copper, iron, all this stuff from water. So this is the thing. And so finally, what we have done, we have taken a sponge. The sponge generally we use for dishwashing in our kitchen. So very common sponge. And we have coated the sponge with our compound. And now, due to coating of this on the sponge is now hydrophobic in nature. So sponge is now hydrophobic in nature. And so, but the sponge now can attract all kinds of oil. So whether it is coconut oil or mineral oil, or kerosene, mustard oil, whatever it is, the sponge now can attract uh, organic oil. And we can use that sponge for multiple cycles to take out the oil, to attract the oil. And then what we have developed, technology. So where if the oil is floating on top of the water, so using a pump and this our sponge, so you can just take out the oil from top of the water. So you can separate the oil from oil water mixture very nicely using this technology. Or this is working because the sponge is now very much hydrophobic in nature, and so it's repelling water but attracting the oil, and that's why from oil water mixture it is particularly taking the oil and using the pump you can separate the oil from the water mixture. And if you have oil heavier than water, so then also you can use this kind of system, and we have shown that. So in that case, you can use the sponge as a mop. So you just dip it inside the water and go close to the oil, and then water will attract to the sponge, and you just take out the sponge and it will work. So you can remove whether the oil on top of the water or whether the oil on the bottom of the water. So you can separate the oil from water using this compound. So with the same compound, we have able to separate metal ion, positive ion, negative ion, as well as the organic compound from the water. So we can clean the water using these things. And we have also applied for a patent, and we are waiting for the patent. And we are developing some new food things with a company using this compound. Okay, and so this is in-field selective detection of explosive, but I think I should keep this part. Yes, so better to go to this part. So this is more interesting. So we have developed a gel that we can use for different purposes. So for formation of the gel, what we have used, that is the pyridine 2,6 dicarboxylic acid dimethylase and potassium hydroxide. So what we have seen that these two things, potassium hydroxide and this pyridine 2,6 dimethylase, in presence of water, they form gel in methanol. So the water is very important for this purpose. So without water, there will be no gel. So we have studied with different compositions, and we figured out that actually 9:1, so 9 part methanol and 1 part water is the best composition to develop this gel. And we have studied with other metal ions, so like sodium hydroxide, lithium hydroxide, the gel does not form. We have tried with potassium carbonate instead of potassium hydroxide. Again, gel does not form. So the potassium and hydroxide ion, both the ions are very important for this kind of gelation. And so once the gel forms, the gel is very robust. So you can handle with bare hand the gel stick. And what we have seen that actually the uh, gel is a thixotropic gel. So if you push some pressure on the gel, it will melt. If you remove the pressure, again it will form gel. So the gel is thixotropic in nature. Uh, we have studied the morphology of the gel. So like all other gel, so there are dense fiber, entangled fiber that actually encapsulate the solvent and help to make the gel. So as I was saying, the gel is very robust and it can take a significant amount of weight. So here is the gel bath, and we put a conical cap containing some chemicals and it's water on top of the gel, but still the gel. You can chop your gel in small parts, and then if you put them together, after few minutes you will regenerate the entire gel bar with the same strength. So the gel is very uh, uh, mm, dynamic in nature. So if you cut them, they can regenerate. And the most important part is that so you can use that gel as a fuel. So how you can use that gel as a fuel? You don't need any particular kind of stove or anything. So you just take the gel on a glass vessel or on a metal or whatever it is, and if you just put fire, the gel will give you the heat and light. So once gel completely burnt, you will get this kind of light blue color powder. And then if you again add methanol and water in that powder, will regain the gel. So this you can use for multiple cycles. But what we have found that actually after 5 cycles, so this property degenerates. So because we are heating the gel in presence of potassium hydroxide, and actually at that temperature, the potassium hydroxide is hydrolyzing the ester function will be present in the gel box, and that's why with multiple cycles after 4 or 5 cycles, there are hardly any ester rather than the acid of the compounds, and that acid does not form gel. But still, you can use this for at least 3-4 cycles, the same compound, just by recharging with methanol and water. And so you can use this kind of gel as an alternate of uh, wax, alternate of paraffin. So you can use them as a candle or as a diya during the Diwali, or you can use them for the heating of your food on camping. So when you are in camping, because the gel you can put in any kind of container. So whether it is a metal container or plastic container does not matter. So you can put the gel in any kind of container, and it's easy to carry. So using that gel, you can get your heat or light when you are camping. You can warm your food and take your food. So all these kind of things are possible with this material. Okay, and so you can use this gel formation technique to remove very little amount of contaminated water from organic solvent. So if there is little amount of water in organic solvent, you can use this gelator to make it the water in a gel and then take it out from the organic solvent. So that's what I was saying. So you can take the gel. Gel is very robust in any type of container. So we have put all this kind of plastic and metal container with the gel. You do not need any particular kind of glass box or anything else. You can just take out a little bit of gel on any surface, and then you can get your heat and flow from the gel. So you can use the gel for outside application. Okay, and so yes, so you can use that gel for Diwali, for cooking, for heating, or maybe a gel like dinner, like a candle dinner. Okay, and last part of my talk. So now I will talk about a molecular reactor. So we all know that in nature the chemistry is going so nicely. There is almost no waste. But in our chemical laboratory or chemical industry, so when we make some molecule, we simultaneously produce a huge amount of chemical waste. And unfortunately, we stored that waste in some part, and finally, in some part of the world, we are storing that waste, chemical waste. Little bit is recyclable, but most are going to contaminate the world. So, can we make a molecular reactor where, like in a biological system, we can make our drug molecule or other important molecule just like cut and paste, and without any waste, without any chemical waste? Is it possible? So that is the question. So a device in which the chemical reaction can take place in a confined, we call it's a nano reactor or a molecular reactor, and actually the space is nanometer. So the confinement is mostly a nano channel. So this is the scheme what I want to say to you. So here we have a nano channel, and then we are loading chemicals A, reactant A, and loading reactant B, and then we are giving our energy so to do the reaction, and it's done the reaction without any other solvent, without any waste. So is it possible? And so the system should be applicable for liquid gas or solid gas system or liquid system. Advantage of this system, this is solvent free, so it will be eco-friendly, energy efficient, and there will be high selectivity, safety, and reliability. So that is the important part of this kind of thing. So for that purpose, we have designed a peptide. So we need a channel that is nanometer in size. So we have designed a peptide with phenylalanine, 4-phenylalanine, and one alpha amino isobutyryl. And we got the solid state structure of the peptide. The peptide backbone is from a 3-10 helical structure in the backbone. So once we put that aromatic function group back, we have seen that actually it's from a channel. So this aromatic groups, so they form a channel, pi channel. So where we can do our reaction. And now loading of different reagents, say loading of toluene, and we see that from solid state structure, so we can incorporate 2 toluene molecules inside the channel. So one is in the channel and another is little bit side. And so this is the crystals of toluene, and this is the toluene molecule inside the channel. Okay, so toluene is not much reactive, so we need something which is reactive. So we load aniline, again 2 aniline molecules that is going inside the channel. The channel is intact, whether it is toluene or aniline, doesn't matter. So again, this is the crystal structure of aniline, and what we find that the aniline molecule are actually in the channel. And then we are trying to do the reaction in the channel. So as we have aniline inside the channel, we thought let's do some halogenation reaction. So try with X2. And if it is a simple amino, we know that there may be monosubstitution, disubstitution, or even trisubstitution, and there are different isomers are possible with the halogenation. There is no control. So first we have done that reaction with bromine, and what we found that our system rupture. So we have system with aniline, with charged bromine, the entire system rupture. And we are very frustrated. So what's happened? So our logic doesn't work. And then we have analyzed that compound, that ruptured structure material with mass spectrum. And what we found that so actually the reaction takes place. So but instead of monobromination, it's dibromo and tribromo product is formed. And as the tribromo product is formed, it's the size in that became very big, the tribromyelin, and actually that ruptured the system due to size explosion. Okay, so then we have tried with iodine, and so iodine is less vigorous to do reaction. And what we have find that now the reaction takes place, we have again take the mass spectrometry, and we found that monoiodination takes place. And here is the mass spectra of our peptide compound, and there are no iodination on this phenyl aromatic gene, but it's iodination only with that aniline. And so what about the selectivity? So there may be ortho or para iodination is possible. And so we have got the results of that iodine, and after reaction, and we figure out that it is basically the ortho iodination technique. So iodine enter in ortho position selectively. Further, we have used this molecular reactor for other reaction as well. So it is not only for the halogenation reaction. So, but we have used this for deep solder kind of reaction. So where we have possibility of exo and endo product, and we have found that only one kind of product is happening due to restriction of size inside the channel. We have also done a Morita-based Hilton reactions, and so we have seen that the channel is helping to increase the product in this kind of reaction. And when the product is formed, the product is insoluble, and so it's coming out from the system and it's precipitated. But the system is soluble, and so yes, this is working fine for other reaction as well. Okay, so I dream that in future there will be an assembly line, like a car assembly line, to produce our drugs and other important molecules. So where there will be minimum waste, just bolt and screw and get your material. And so these are the issues with this kind of biology adaptive system that also we have to address. So if you use nanomaterial, so also you are polluting the world. So the nanomaterials, once you prepare, so this may be dangerous for future if it is properly uh, taken care of. And that might cause new disease, health hazard, and obviously we are in the early stage. So to know about the toxicity of this kind of nanomaterials, we need a longer time. So probably in future we can say about the toxic effect of lab on chips of this kind of nanomaterial. And another thing is that this kind of material may be used for biowarfare, biowarfare and terrorism, but that is not in our hand. As a scientist, we can think about the betterment of the civilization. We can produce something for good purpose, but obviously the people with ill mind, they can utilize it for the bad purpose. Okay, so with that, I will stop here. So I thank my students so who have done the entire work. So as from the data you can see it's a huge amount of work they have done, and so these are the students who have done the work. I thank them. And for financial support, I have support from CSIR, from DST, from Alexander from Humboldt Foundation, and obviously from Azad, Kolkata. And if you have any question, I will happy to answer.
Thank you, Professor Haldar, for this fascinating lecture covering several topics and at the interface of biology, chemistry, and medicine, all these parts, and sharing with us the ongoing brilliant result that are coming out of the research works by your group. So I think students and the participants have enjoyed a lot. So now may I ask the participant for the discussions. If they have any questions, please put it on the chat box or in the question answer box. Then, okay, I think we have already one. So it's from same three students that which nanoparticle is used for cancer treatment? Specific is there?
For cancer treatment, you can use this platinum nanoparticle. But nowadays, there are many hybrid nanoparticles that are used for cancer treatment. And actually, it is not only the nanoparticles, it is the embedded drug. So you have made a nanoparticle and then embedded a drug on the nanoparticle. And together, this can fight.
Sir, can you keep your microphone?
Oh, yes. Sorry. So for this cancer treatment, actually, instead of using a single nanoparticle, now they are using the nanoparticle embedded with drug molecule, and so that hybrid material they are using for cancer treatment. So it is not a single simple nanoparticle. But obviously, there are reports that you can use the gold nanoparticle or platinum nanoparticle specifically for some specific cancer.
Okay. So there is many more to start with. Is the POSS, the post-appended diphenyl alanine, sustainable, and the sustainability of this hybrid can increase?
Yes, the hybrid material is sustainable, and that is my concern, because if it is not degraded by fire, then I don't know what the toxicity it will cause in future. So that was the concern in my last slide. So we are developing the material, but we don't know about future toxicity of this kind of material. So this is very much sustainable.
The question is how are these nanoparticles selected?
That depends on your purpose. For what purpose you want to utilize the nanoparticle. See,
Sir, for the treatment of cancer, sir, it's the question, sir. For the treatment of cancer, like how are these nanoparticles selected?
now, so that depends on which kind of cancer you have, and secondly, what kind of treatment you want. So if you want just a like a therapeutic chemotherapy treatment, so in that case you need to combine all that chemotherapy chemicals on top of the nanoparticle. So in that case, the nanoparticle should not be active. Nanoparticle should work as a carrier, and your chemotherapeutic material will cover the nanoparticle or maybe encapsulated on the nanoparticle, and then it will work. Otherwise, if you want that your nanoparticle directly used against cancer, then you have to develop particular shape and sizes of gold nanoparticle or platinum nanoparticle. So that's actually used to fight against cancer. And again, if you want to develop some hybrid material, then you have to utilize different factors in the cancer cell. So some people, they use the heat. You know that in cancer cell actually it's produced a huge amount of heat rather than the normal cell. And so people use some heat sensitizing chemical to develop that kind of nanoparticle. So the nanoparticle in presence of that amount of heat will activate and destroy the cancer cell. Otherwise, say for our purpose, we have used hydrogen peroxide. So we know that in cancer cell, there is a large amount of hydrogen peroxide than the normal cell. So we use that particular property of hydrogen peroxide. So the hydrogen peroxide will rupture our nanoparticle and release the help to release the drug. So like this, so you have to make your target accordingly.
Okay, thank you, sir. There is another one. How can quantum dots improve their efficiency?
So quantum dots, actually the efficiency decreases due to defects. So if you can improve or if you can decrease the defects, actually you can improve the efficiency of the quantum dot. And that defects you can decrease by using different stabilizing molecules. So by using different stabilizing agents. So it's a trial and error method. So you have to try with different stabilizing agents and then study the efficiency of the quantum dot.
Okay, sir. Another one, what is the role of the dendrimers in drug delivery?
If you remember the structure of the dendrimer, it is actually a very big molecule, like a network, like a net. And so inside the molecule, there are a lot of cavities. Some cavities are hydrophobic, some cavities are hydrophilic. So if you have a hydrophobic or hydrophilic drug, you can wrap that drug with your dendrimer molecule. So, and by that way, the entire dendrimer will work as a capsule for the drug.
Then another question, sir, how H2O2 acts as a drug carrier?
Now, H2O2 does not act as a drug carrier. So H2O2 is not very stable. So if you have H2O2 and it will break into H2O and oxygen, atomic oxygen, so very active oxygen. So you cannot use H2O2 as a drug carrier. At least I don't know any example.
Okay. Then another one, although nanoparticles causes health hazards, then why are they used in cancer treatment?
So at this moment, with existing drugs, so there are different type of cancers and they react differently with different drugs. So in some cases, if you cannot cure some cancer with the existing cancer drug, but nanoparticle can work, so it's better to use nanoparticle for this moment to relieve the patient. But obviously, the nanoparticle, we don't know yet what is their toxicity and how they will affect the environment in future. Obviously, there is a question mark. But for immediate release of the patient, so we can use nanoparticle if it is required.
Thank you, sir. There is another one. Is artificial photosynthesis possible?
Yes, yes. So artificial photosynthesis is possible. Many groups are working on that. So they are making material that's helping artificial photosynthesis. But still there are some limitations. So not too much popular yet or industrialized yet, but hopefully in future, so we will overcome that difficulty, and it's possible. Artificial photosynthesis, I think it will possible industrially.
Then what is the transdermal drug delivery and the role of carbon nanofiber in this process?
So it is not the carbon nanofiber rather than the carbon nanotubes. So basically nowadays there are some creams are coming out containing these carbon nanotubes, and so these carbon nanotubes, they just pass through like a pin. They just pass through the top layer of the dump of your skin, and with that nanopores of the carbon nanotube, the drug can go inside the skin. But this is also in very early stage. Probably you have heard about a black color that is patented in UK. They are using carbon nanotube, and in a particular medium, the carbon nanotube are actually perpendicular to the surface. So whenever there is some light on the carbon nanotube containing black color, no light is coming out. So it is very, very black color, and that is patented in UK. And so like that system, if we can develop some cream where it will help to actually make this carbon nanotube perpendicular to our skin, and then it will pass through the skin, and it will help to pass the drug molecule through the nanopore of the carbon nanotube. So otherwise, if it is parallel with the skin, it is not going to help you.
Okay, thank you, sir. I think you have nicely addressed the question, and the participant have realized that. And there is another one, last one so far, that what are the differences between nanoparticles and quantum dots? Is there any different approach which are more effective and less health hazards than nanoparticles?
Basically, quantum dots are also a kind of nanoparticle. So we said that the nano range is just 5 or 10 to 100 nanometers. Nowadays, people are considering from 5 to 100 nanometers. So basically, most of the nanoparticles, they are in the range of 10 to 100 nanometers. But this quantum dot, they are in the range of 2 to 10 nanometers. So that is a size distribution, difference of size between these two. Otherwise, you can say a quantum dot is also a kind of nanoparticle.
Tapasvi, you're muted, sir. Unmute your mic, sir.
Oh, sorry. There is another one, sir. It should be nano dot, I guess, or nano boards. I don't know. But are there any negative effects of using nano bots? Is it bot? I think nano dot.
I think he's talking about quantum dot. So he said about nano dot. Yes, mixed together. Obviously, there are side effects. So you know that cadmium sulfide, so that is toxic in nature. So even if you make it in a nano size, it is not totally out of toxicity. So we don't know in future if you accumulate a lot of nanoparticles in some point, that's obviously going to be toxic for the environment.
Then another one, sir. We know cancer is an unusual growth of malignant cells. If nanoparticles treat cancer, can it be used in other diseases like normal cyst, tumor, which are not malignant without operating them?
No, for nanoparticle that used in cancer drug, it is not only the nanoparticle. So there are some cancer-specific ligands attached with the nanoparticle, and that's why this nanoparticle will go to particular cancer cell, will go to particular cancer site, and then it will release the cancer drug or anti-cancer drug, or it will act as an anti-cancer agent. So if there is no specificity, then that is not a drug at all. If it acts against your normal cell, you cannot use that.
Okay. I think sir have been kind enough to answer all the questions from the participant, and I hope they have enjoyed the session and the queries that have raised in their minds that have been answered quite well. So we think this, I think, as there is no more questions so far, I would like to thank again Professor Haldar for his nice lecture and taking your time to share with us your research works. And thank you again, sir.
Thank you very much. Thank you.
Thank you. Thank you. So I think for the participants, this is in the chat box, you can find the attendance come feedback link. So you are requested to fill it up. And I think we are formally good to close this session 1 of day 5 with this illuminating lecture session with so many aspects of chemistry at the interface of biology. And as the program will go on, so in the second session, we will be meeting at 3 p.m. sharply. We have 2 lectures in the second session of today. So till then, I think I should say goodbye, and we will see. Yeah, goodbye, sir, and thank you, sir. And we will meet at 3 p.m. sharply then. Prem, is there anything more to announce? I guess no.
No, sir. Sir, our next speaker is from, I think, Spain, sir.
Yes, yes. So we will. So it's a quite time difference, 4.5 hours